I think it's time for me to start. Is that okay? You guys ready? Okay. So today we finally will be able to talk about Drinfeld modules, and I want to stress that the Carlitz module that I've been talking about is a Drinfeld module. It's just like a special one, so we gave it a special name. It's historically the first one that people talked about. It was first studied, like I said last time, by Carlitz himself, although he did not know what he was doing. He was only studying this exponential function that I gave you and noticing that it had some properties like the classical exponential function, and wrote several papers about this, maybe like 3 or 4. And it's only late, and that was in the 20s or the 30s, and it's only in the 70s that Drinfeld came along and kind of unified the theory, Drinfeld modules of any rank, and then that Hayes wrote this very nice, extremely readable paper about the class field theory that goes with the Carlitz module. So we have already started Drinfeld modules. I just have been calling it the Carlitz module because it's a special rank 1. So why would you care about Drinfeld modules apart from that'll make the next hour of your life better and you're mathematicians and they're awesome? Say your friends and family are asking you. You can always show them this video. We just need a minute. It's from 24. Hopefully that doesn't date me too much. Oh, that's not loud enough. Don't. That's the only thing they say about it. So hopefully you could hear it. Wow. It's not true. So anyway, if you want to show this to people, it's on my husband math vlog. We actually had to get released from Fox to post this because it infringed on their copyright, but they let us. Okay, so you can use Drinfeld modules to disable centrifuge if people are about to explode them to bring about a nuclear holocaust on American soil. Tell that to your parents. Okay, so we're going to continue today with the Carlitz module. There's a few more things that I want to tell you. So here's my plan. Is to go kind of medium fast through the Carlitz module to keep as many of you here with me, and then go kind of fast through Drinfeld modules of higher rank, and then talk about Drinfeld modules of rank 2, which are near and dear to my heart. And at that point, if you don't know about elliptic curves, maybe a lot of it will be very confusing, but hopefully it'll give you stuff to Google and think about afterwards, and you'll be like stimulated to further study rather than hopelessly confused. And if you're hopelessly confused, let me know. Okay, so Carlitz module, again, just to reiterate, it is the Drinfeld module of rank 1. Why do I say that? Over an algebraically closed field up to isomorphism, there's only one isomorphism class of Drinfeld modules of rank 1, so you can, call it the Drinfeld module of rank 1. And I'm going to present this in the shape of my analogy, where on this side I'll have the number field stuff, and on this side I'll have the function field stuff, to try to keep your mind thinking about both sides and give you something to think about. So, like I said, on the number field side, we have the exponential function, which is given by arguably the simplest Taylor series. And on the function field side, we have the Carlitz exponential function, which is given, again, by maybe the simplest Taylor series. And I've talked yesterday about the analogy between, like, this is the size of an integer of size n, and that's the size of a polynomial of degree n. And this is the product of all the numbers less than or equal to n. This is the product of all the polynomials. Okay, so I should have stressed that. In my mind, like, whenever I write a, I mean a polynomial. So a monic, the degree of a is n. Okay, so this is arguably an analog of the exponential. Of course, I'm not taking the things of lower degree, but that's something that's done a lot in function field, to focus on 1 degree, because there's already many polynomials of 1 degree. And the monic is the analog of thinking of positive, because you just want to not multiply by units. Then you have more stuff than you need. Okay, so we both start with this, like, exponential functions on both sides. And then what is true, right? Well, this one usually in over the complex numbers, we say, like, it's holomorphic, right? It doesn't have any poles or anything. On this side, the word that I've seen used is entire, but you could say holomorphic. You could say regular. There's many ways to talk about functions that don't have poles. So they're both, well behaved. And for this one, that was an exercise after lecture 2. Once we knew about convergence of Taylor series, we could prove that actually pretty easily. If I think of the exponential function as going from C to C cross, so if I avoid 0, it's surjective. This function is also surjective, this time on all of C infinity. That's not something that I'm going to prove, but it follows from general non-Archimedean analysis principles. So a non-constant entire function with respect to a non-Archimedean valuation is always surjective. So it's just kind of like analytical stuff. And then on this side, I can ask about the kernel of the exponential function, okay, by which I mean, just z, such that the exponential of z is 1, right? I don't want 0 because I'm mapping to C cross. Also, I would get nothing, okay? And hopefully, you know that this is all the integer multiples of 2 pi I. And what's more, 2 pi is a transcendental number. Well, on this side, I could do the same thing. I could ask for the kernel of the Carlitz function, which here is going to be z, such that ECZ is 0. Because here I'm still thinking of all of C infinity. And EC is an additive function. And it turns out, okay, that this is some number which we call pi tilde, not perhaps, because of the analogy, times FQ brackets T, which are my integers. And this is a specific transcendental number. I have formulas for it, which would not, like, people come up with formulas for it. It's like a thing, right? Just like people like to try to write, expansions for pi and formulas for pi. It's the same kind of thing, but, it's a transcendental number. It is what it is. But what I want to bring up, right, is that this is a rank 1 lattice in C, and this is a rank 1 FQ brackets T lattice in C infinity, right? It's all multiples. Like, this is all polynomial multiples of one number. So that's, another analogy between these two, that their kernel as rank 1 as a module over what we consider to be the integers. And then and how do you prove this? Sorry, I'm not going to prove it, but I want to say a little something. The way you can prove this, the way that's not too difficult to prove this, is to actually write this exponential function as a product over the elements of this lattice, 1 minus z over that. And it's many tedious steps of algebra to do this, but it's not super difficult. You first do you do like a finite product over the elements of this, just the polynomial ring, and then you compute at each step what that finite polynomial is as a sum, and then you let the degree go to infinity, and you get a product, where here you're taking the product over the polynomials, but then you got like some ugly factors in here, and so you're like, well, if I wasn't, like wanting my product to be over the polynomials, but like over like some multiple of the polynomials, then I would get this lattice. So anyway, I don't know if that helped any. It's not super complicated, mostly tedious, and I want to move on. But we'll have these expressions come up later. So in a while, when I introduce more general exponential functions, I'll do them in terms of these products, because then it's really easy to see their kernel, right? If lambda is in the lattice, and I should say here, I don't want lambda to be 0, okay? 0 is definitely in that lattice, because it's 0 times pi tilde, but I don't want to divide by 0. So that's why there's a little z in front, and then all the other non-zero elements of the lattice. Okay, so if I plug in lambda to be in the lattice, then I get 1 minus 1, so that's a simple 0 of this function. And that's how you get the kernel from it. Okay, so you have that. And then the last part, which I kind of talked about, on this side, we have that the exponential of n times z is the exponential of z to the n for any integer. And what we'll see on this side, which we have kind of started working out, and if you did the exercises from yesterday, you've started working out, we'll see that for all a in FQ brackets t, there exists a polynomial CA, which is actually in the twisted polynomial ring in tau with coefficient. So I always call this ring A, and I've been trying to avoid introducing this notation to not overload things, but then I used it. So that's all I mean. Okay, there's a polynomial in tau with polynomial coefficients such that if I take EC of AZ, right, which is the analog of doing this, then what happens is this polynomial to ECZ. Okay, and we'll talk about this polynomial a lot more. I'm just continuing the analogy for a little longer before I say more about this. Okay, and this assigns on this side, right, to each n some polynomial z to the n. And here I'll think that this assigns to each a this polynomial CA. And that's the crucial bones of a Drinfeld module. It's an assignment of a polynomial to an integer. For each integer, you get some polynomial. Where here I'm using integer loosely, right? For me, integers are polynomials because they're integers in the function field, right? Here, integers are integers, like 1, 2, 3, right? And you get a polynomial out of it. So here for each integer, I get a polynomial over my integers. And that, when I define Drinfeld modules, that's what I will say. A Drinfeld module is an assignment to each polynomial, like to each integer, of some other polynomial, some further polynomial. And then we look at the torsion points. Right, like you fix n, you look at z to the n is equal to 1. These generate abelian extensions of Q. It's actually much stronger than that. It generates all the abelian extensions of Q. The roots of these polynomials, the roots of unity, generate every single abelian extension of Q.
Quadratics on the side of it. Cover all.
Right. Sorry. I mean, like, every abelian extension is contained in one of these, not like literally there are no other abelian extensions than cyclotomic polynomials. Sorry. Yes. There are 2 quadratics you can get like this, but not the other ones. And so here on this side, we'll do the same thing. We'll consider these torsion points. Right, so now there'll be CA of Z is equal to 0, and this will generate most abelian extensions of FQ round brackets T. And I'll be a lot more precise about like what I mean by most. Okay, so that's the analogy, right? That's like what's happening. This is the way in which the Carlitz module is an analog of exponentials and this, this whole story. Okay, so let me dig in this side of the paper a little bit more, right? So last time we had, as a proposition, that EC of TZ was TECZ plus ECZ raised to the Q, okay? And I just want to remind you, right, I'm working over FQ brackets T, so this T is that T and this Q is that Q, right? Like I'm fixing this polynomial ring, so Q and T have a meaning here. Okay, and the proof is extremely pleasing and not at all scary, so I will do it. So you just plug in like a hopeful person, like this. And then what I'm going to do is I'm going to compute EC of TZ minus T, EC of Z, and hope that I get EC to the Q. So that's the sum, n is equal to 0 to infinity, of T to the Q to the N, Z to the Q to the N, minus T, Z to the Q to the N, all over dn. Okay, because here I'm multiplying T outside, so I only get this much. And I actually noticed that if n is equal to 0, Q to the 0 is 1, so I get TZ minus TZ, so I get 0. So I'm going to just start my sum at n is equal to 1 now. And I get T to the Q to the N minus T, Z, Q to the N over dn. And here, okay, I'll have like a little aside that dn is equal to T to the Q to the N minus T times dn minus 1 to the Q. So that was in the lecture 2 exercises. If you got like bogged down in the weeds of like the dn and the ln and the square brackets and thing, you've played with this a bunch. And if not, just believe me that this is true. But in either case, if I move this stuff around, I'll get... I'm just such a good taper, and I tape it very well. Okay. I'll get that EC of TZ minus T of ECZ is the sum, now starting at 1, of Z to the Q to the N divided by D sub N minus 1 to the Q. And now I use that I'm in characteristic P, and P is a power of Q. Did I say it the wrong way? Yeah. You know what I mean. Then Q is the power of P to get this expression, right? I can just extract a power of Q through a sum, as in the dreams of your calculus students. And now re-indexing my sum, right? I very cleverly am now starting at 1. This is easy. EC of Z to the Q, and I'm done. Okay, so it's like not a big deal at all to say this. But from this, as a corollary, we get everything. We get the action of every other polynomial, okay, by recursion and FQ linearity of ECZ. So the corollary is for all A in FQ T, there exists CA, and it will have integer coefficients, and it will have only x to the q and x to the q squared and x in it, such that EC of AZ is equal to CA of EC. See? And you get like extra properties even out of this. Like, it's not just any random polynomial. I mean, it's not. It's a specific one. There's a unique one. But it's very nice. And how would you do that? I'll just do like a quick, how would you compute one of them? Right? So if A were, for example, like t squared plus 2, okay, if I wanted to know what EC of t squared plus 2 Z is, right? Like I want to know what polynomial I get on the other side. Well, first I use FQ linearity to say that this is EC t squared Z plus 2 ECZ. Okay, and why is this FQ linear? Is because my power series is in Z to the Q, and so every finite sum in this power series is FQ linear. And so as I let n go to infinity in the sum, it's also FQ linear. So that's why we spent all this time talking about FQ linear things, so that I could have this. And then, okay, so here, that's it. But on this side, I can use like a little trick. Right, this is T, EC, TZ, plus EC, TZ to the Q. So I'm thinking of T squared Z as T times TZ and applying what T does, right? I said that EC of T times something was T times EC of that thing plus EC of that thing to the Q. So I'm just like pulling one T out at a time. Plus 2 ECZ. And then now I'm going to pull out the other T. So this is T squared ECZ plus T ECZ to the Q. And then I do the same thing here. This is T to the Q ECZ to the Q plus ECZ to the Q squared, right? Because I already had a Q and then I get another Q. And I have plus 2 ECZ. And now I'm just going to collect all my terms. So I have t squared plus 2 ECZ plus t to the q plus t ECZ to the q plus ECZ to the q squared. So this is c sub t squared plus 2 of ECZ, where c sub t squared plus 2 is t squared plus 2 tau to the 0 plus t to the q plus t tau plus tau squared, right? Like when I plug in ECZ, I get just ECZ, ECZ to the q, and ECZ to the q squared. So this is the polynomial that I'm associating with t squared plus 2. The polynomial that tells me what happens to ECZ when I plug in t squared plus 2 inside of it. So what I want you to notice is first, this linear term is t squared plus 2, and I started with t squared plus 2. It is not a coincidence. That will always happen, which you can trace out, right? Like a t came out, and then the other t came out, and the 2 came out, and that would always happen. And then another thing that will always happen is that this is degree 2, and that is degree 2 in tau. That will also always happen because, right, no matter what the degree is here, I'll have to kind of apply this trick, like, you know, if it's degree n, like n times, so I'll end up with like a tau to the n at the end. And another thing that's like not so apparent from here, but actually whatever coefficient is from the highest power of tau is always going to be the leading coefficient of this polynomial. So this has leading coefficient 1, so there's a 1 here. And if I had been thinking a little better, I would have picked something with not leading coefficient 1 so you could see it come out. But you would see the leading coefficient of the polynomial come out at the other side. And then there's formulas even for the coefficients in the middle. I mean, like, people have studied this a lot and gotten like all kinds of like pleasant things. So if you want to relax one evening, you can just compute a bunch of these. It's like very soothing, I think. Okay, but that's what I mean, right? When I was saying, way back here, right, that to every polynomial I would associate a further polynomial. This is this assignment that I have, like the polynomial t squared plus 2, and I assign to it this polynomial here. And it'll always have integer coefficients. There's no way I'm going to divide. Like you've seen what I was doing. That would never happen. Okay, so I did that. Awesome. Okay, and so the last thing that I want to say, I forgot to say something. Okay, so let's go back to our analogy for a second. Right, the torsion points z such that z to the n is equal to 1, right? These are isomorphic to z mod n as a z module. And here, the torsion points of the Carlitz module, they'll be isomorphic to fq brackets t mod, the ideal generated by the polynomial a, as an a module. Okay, on this side, the a module structure. Oh, sorry, I keep saying a because in my head this is the ring A, right? I should have just warned you of that, but I'm trying not to do that. So as an fq brackets t module, not a this little guy, a the big guy, a this ring. So as an fq brackets t module, these are isomorphic, but here the module structure is given by the Carlitz module. And here the module structure is given by multiplication. On this side is given by multiplication. On this side is given by the Carlitz module. And actually, if you care about these as group schemes, you really shouldn't write this. You should write mu n, because if in characteristic dividing n, this is not separable, and the same thing happens on this side. So if you had p dividing this polynomial a, or pi dividing this polynomial a, an irreducible polynomial, and you were talking about this modulo pi, whatever that will mean, then this would be also inseparable. So there's a lot there's a lot going on there with this analogy. Okay, and then let me tell you the good theorem. Maybe I'll just skip the Drinfeld modules of rank 2. There's just so much that I want to tell you. Okay, I'm going to attribute it to Hayes because he's the one that wrote it like this. So the extensions of FQ round brackets T generated by these torsion points plus the constant field extension Okay, so here I'm talking about stuff like FQ squared, T, like that kind of stuff. So I could extend just the field of constant in my polynomial ring, and that would also be an abelian extension, so I have to count those, contain all abelian extensions of FQ brackets T that are not wildly ramified at infinity. Okay, so it's not quite Kronecker rubber, right? They don't contain all the abelian extensions. You have to have like several lines of caveats. So you need constant field extensions also. And then all of these extensions that I'm constructing with this Carlitz module, they're all tamely ramified at infinity. So I won't get any of the abelian extensions that are wildly ramified at infinity. But that's not that big a deal, because if I want those, I can start over with 1 over t instead of t. Right, so I started with everything like, you know, my base ring was FQ square brackets T. I could start with the polynomials in 1 over T, and then this field, FQ round brackets T and 1 over T, is isomorphic to, I mean, it's the same as FQ round brackets T. So the whole thing would go along the same way. I would construct, you know, a slightly different Carlitz module, and I would get, you know, different division points, and these would generate the extensions that I'm missing that are wildly ramified. Actually, you don't even have to pick 1 over t. You can pick any degree 1 place and still have it work. So, and then I just want to say, right, some of you are concerned about other function fields, right? So if you know about this theory, what I've done secretly in my heart is I started by picking the curve P1 and took its function field, and then I picked a point of degree 1 on that curve, and my ring was all the functions regular outside of that point, and I just went from there. Say you had a different curve X that you loved, and this curve had a point on it, not necessarily of degree 1, then you could do everything that I've done. You could create a Carlitz module for that function field and that ring of integers, and you would get extensions of that function field that are abelian and tamely ramified outside of that place. So this just does like all of the class field theory of every function field. You know, like every abelian extension, it can be gotten that way. You know, possibly by like switching places if you want like all the ramification. But okay, what I'm trying to say is that like everything I've done was like the babyest case of like P1 as my curve and a degree 1 place as my place. But you could go wild with this. Okay, so that finishes what I want to say about the Carlitz module. So in my last 15 minutes, I'm going to talk about Drinfeld modules of rank 2. So I'm just going to skip general Drinfeld modules. Hopefully that's not the ones we need to stop those reactors. But if so, we'll just be stuck. Okay, so I'm going to make my theory a little bit more general. So I'm going to let K be an FQ brackets T field, by which I mean there exists a map from FQ brackets T to K that's just a ring homomorphism. Okay, that's all I want. You might have thought right before when this was like FQ rounds brackets T, that was just the inclusion, or when this was C infinity, that was just the inclusion. That's great. But you might also want to think of quotient rings, right? You might want to think of taking your integers and modding out by, say, like a prime polynomial, and then that would still be a field because you're using a prime polynomial, and that would be an FQ brackets T field. And that would be okay for you to do. So here what I'm setting up, right, is kind of like when you're talking about elliptic curves, you can talk about elliptic curves like over Q and over the complex numbers, but you can also talk about elliptic curves like over FP or over FQ, like a finite field with a finite field. So here I want to set up like any kind of field that I want to talk about. And then definition, okay, a homomorphism of FQ algebras P from FQ brackets T to K tau, which is the endomorphism of FQ linear the endomorphisms of the additive group that are also FQ linear. So this is what we talked about before. So that's just a fancy way to say that. I want over K stuff that's additive and FQ linear. We talked about that. Those are just the polynomials and tau. So you can just think polynomials and tau. Okay. Is a Drinfeld module over K, if and only if the first thing that I require is that phi A prime of Z is equal to I of A, right? So phi sub A is like the C sub A from before. Is if I take A and I map here, I get some polynomial, and I can take its derivative. I want its derivative to be I of A. So before, right, I said the linear term, when I started with t squared plus 2, the linear term was t squared plus 2. That's what I'm saying here. The linear term has to be A. Well, okay, sometimes A is not in the field K because it might be in the kernel. So I just want it to be the image of A under this map. Okay, and for some A, phi of A is not A tau naught. Right, so I don't have just like the linear polynomials.
What is that?
It's a derivative from last time. Yeah, that's a polynomial, right? And I just differentiate it. I mean, I'm just saying the linear term, right? This is the same as saying that phi A of Z starts out with IA Z plus other stuff, because all the other stuff will disappear when I take the derivative. And I say it like this because like fancy people like to talk about like this tangent space at 0.
Sorry, what did you say? What did you say?
Oh, Z, right, so here this is a polynomial in tau, but tau is Z to the Q. So I have my base polynomial ring in T, and then I'm taking polynomials in those, so that's my indeterminate.
A is a polynomial in FQ bracket T. A is a polynomial.
The coefficient, yeah, A is in FQ brackets T, but phi of A is the polynomial in K in two variables, kind of, you could think. Right, so sorry, let me just write that down, right? So, like, let's go back to the situation when K was this, right? Then phi of A of Z would be like the coefficients of the polynomial are in the field K, but it's a polynomial in an extra indeterminate Z. Yeah, but actually I'm requiring that it's contained in the space spanned by Z, ZQ, etc. Right? So that's why I write tau instead. Okay, and this Drinfeld module is of rank 2 if and only if the polynomial associated to T is of the form T tau naught, right? So that's forced. I have to start with T plus some number that I'll call G times tau plus delta times tau squared, and delta is not 0. Okay, so compare to the Carlitz module, where CT of Z was T tau naught plus tau, that was rank 1, right? Because T was associated to a degree 1 polynomial in tau. So then a rank 2 Drinfeld module associates to T a polynomial that's degree 2 in tau. A rank 3 Drinfeld module associates to T a polynomial that's degree 3 in tau, etc., etc., etc. Okay, so, and assigning T to some polynomial fully determines the whole map here, because it's a homomorphism of FQ algebras. So it's linear in FQ and multiplicative. So you can just figure out, like I did for the Carlitz module, right? If you wanted to know what phi of T squared Z was, you would just do the computation just like I did. And you would figure that out, and then, etc. So usually when we talk about a Drinfeld module, we tell you only where T goes, because that's enough. Like the image of one, right, generator of this FQ algebra is enough to tell you where everything goes. So you just say that one. Okay, what do I want to tell you? Oh, I want to tell you what's an isogeny. So Drinfeld modules of rank 2 behave remarkably like elliptic curves. Let me tell you what an isogeny is. So definition. An isogeny is a non-zero. Okay, do you want 0 to be an isogeny or not? You want it to be in the endomorphism ring, so it's a ring. I don't know. It's a non-zero polynomial in K tau such that, an isogeny from one Drinfeld module to another Drinfeld module. So my other Drinfeld module I'll call psi. Okay, such that, and I always mess up the order, but I will figure it out. Psi sub A times P is equals to P times phi of A for all A. In FQ brackets T. Okay, where here, this multiplication is composition because it's multiplication in this non-commutative ring, K curly brackets tau. Okay, and an isomorphism is an invertible isogeny, right? Okay, what polynomials in here are invertible? They have to be of the form P is CZ for some Z in K. Or maybe I want to allow coefficients in K bar to get all of the isogenies. So let's figure out when two Drinfeld modules of rank 2 are isomorphic, so I can end on something that I think is very nice. I can give you the moduli space of Drinfeld modules of rank 2. When are psi and phi isomorphic, right? And you'll notice how much simpler it is to check this than it is to check that two elliptic curves are isomorphic. If you've ever checked that two elliptic curves were isomorphic, it's not something you cram in 3 minutes at the end of like the full week of math, right? But I can do it with Drinfeld modules, right? Well, what I want, there should exist some number C in K bar with C. I always forget the composition order. I mean, it doesn't really matter. Phi t times CZ is equal to CZ times phi t. I'm just gonna look at what I wrote down. There we go. Okay, so let's start with this side. What that is. So this is t tau naught. I'm gonna switch to tau notation because it helps me think of composition. Plus maybe g2 tau plus delta 2 tau squared times c tau naught. And then remember, multiplication is composition, so I'm going to put, I'm going to, I think of this like moving that way, like inside my polynomial. So I get t, and then I apply tau naught to c tau naught, but that does nothing because that's just the identity. So that's t c tau naught. Okay, that's not so bad. And then I apply tau to c tau naught, right? So I get g2 c to the q tau, right? Because my c was on the right and it had to move like through the tau, so it picked up a power of q. And then plus, right, like this one, like I move it like kind of through my tau squared, which raises to the q squared. So plus delta 2 c to the q squared tau squared. So that's what the left-hand side is. And then the right-hand side, right, is c tau naught times my other Drinfeld module. Okay, but here, right, when I move stuff to the left, like tau naught does nothing. So everything will just pass through. So this is tc tau naught plus g1c tau plus delta 1c tau squared, right? Because tau naught is just the identity. So that multiplication doesn't do anything weird. Okay, and what I want is for these things to be equal, right? Like this left-hand side and right-hand side. Okay, well, TC is equal to TC without me doing anything. But I want G2 C to the Q to be equal to G1C. And I want delta 2 C to the Q squared to be equal to delta 1C. And so if how do I want this? I'm going to write this as G1. It doesn't really matter, but that's C to the Q minus 1 G2. And delta 1 is C to the Q squared minus 1 delta 2. Right? That's what I need. I need both of these to be true at the same time. So if you've worked out, right, when are two short Weierstrass models for elliptic curves isomorphic, and you had the coefficients, you got the same kind of equation from here, right? Like the C4 of one equation has to be like u to the 4 times the C4 of the other equation, and the C6 of one equation has to be u to the 6 of the other equation. This is exactly the analog. These coefficients are modular forms, just like the coefficients of the Weierstrass model of an elliptic curve are modular forms. And in fact, this coefficient G is an Eisenstein series, just like those C coefficients are Eisenstein series. This one, delta, is a cusp form, just like R delta is a cusp form for elliptic curves. It's a cusp form of weight q squared minus 1. This is an Eisenstein series of weight q minus 1. And then, to just finish blowing your mind, well, okay, so then looking at two Drinfeld modules, how can I tell they're isomorphic? I need a quantity that's invariant, right? These coefficients are not invariant. What is invariant? Well, we were very creative. We called it the J invariant. But that's the coefficient G to the cube plus 1 divided by delta. If you look at this ratio, right, and look back at how the G and the delta changed under isomorphism, you'll see that this is invariant under an isomorphism. So this is an isomorphism invariant of the Drinfeld module. And in fact, it completely classifies Drinfeld modules over algebraically closed fields. So over an algebraically closed field, the moduli space of Drinfeld modules of rank 2 is just the J line, just like it is for elliptic curves. And this delta is not 0. Remember at the very beginning, right, I said a Drinfeld module delta was not 0. And so the same thing, right, is like if you want to compactify it, what do you add at infinity, right? What's the, like, you know, J is infinite. Well, that's when delta is 0, right? And you can see it from here. And so what's the degenerate rank 2 Drinfeld module? It's the Karlitz module. So for me, when I was a grad student, I read this sentence, and I think it was Katz Major. They said, oh, and then as you move towards the cusp on the moduli space of elliptic curves, the group scheme degenerates to GM. And I was just like, what the heck is going on? But here, you can see the Drinfeld modules of rank 2 degenerate to the Karlitz module, right? It's just like, what happens? Well, delta gets smaller and smaller and smaller until it's 0, and then you have a module of rank 1, which has to be the Karlitz module, which plays the role of GM in this theory. So a lot of stuff that's like kind of more opaque for elliptic curves, I think, is like very apparent for Drinfeld modules of rank 2. And like I got very excited last night. I have pages and pages of other analogies. Like if you know about the analytic uniformization of elliptic curves over a local field, you know, like over C infinity by this Q parameter, like we have that. If you know about the canonical subgroup of an elliptic curve, we have that. And they're all like a lot easier to study in this case, or like at least to define in this case. So it's an extremely productive line of study, like stuff you want to know about elliptic, or stuff you know about elliptic curves, you can try to prove about Drinfeld modules. That was actually my PhD thesis. It's like, take a paper about elliptic curves and like say what it says in the Drinfeld setting. So I hope that this encourages you to study both elliptic curves and Drinfeld modules, because there's so much interesting stuff that you can figure out. But unfortunately, I'm done, so we won't do that with me.